Looks like we can start class. Welcome back, everyone. Well, I have a couple announcements to start us off. First of all, I've returned some of the exams, the ones that were taken in person. But like I mentioned over the weekend on the forum post, the ones that were for this section of the class, the online section, that one's going to take a bit. They still have not fully scanned all the exams from the Pocatello Testing Center to email over to my address. Once that happens, I'll let you know, and I'll also begin grading those. It shouldn't take me too long. I'm hoping I'll get them sometime middle of the week, and I can begin grading them in the middle of the week. If the worst case scenario is we're probably going to be grading them on Friday if they get those exams towards the end of their work week. That's something kind of strange about this section where we're running through the Pocatello Testing Center. We have to go by their constraints, whatever they may be. So sorry for any frustration on the delays on getting your exams back. For folks who are here in person, I do have your exams. Don't hesitate to grab them for me before classes or after class is over. I'll make sure to get it to you. And if you did take the exam in class, but you're just not here today, or if you don't typically come in person, send me an email and I'm happy to scan it and email it right back to you. After the exams are all fully graded, you'll see right over here, we'll have the solutions posted so folks could take a look at it. And after grades are put in, you can come right up here and take a look at your grade at any point. And we're at that point on the course where every time I grade something new, any new element, your course grade here, your overall grade for the class is going to revise pretty much each weekend as well. So it's a good place to come by, double check everything in there. Well, that's our announcements for the exam. Mainly it was sorry for the delays. It's going to take a little bit of time to get through those. Any questions at the moment? Okay, other things to mention is we're on, I believe, example 3 of these notes here, but I did make a revision on example 5 part B and somewhere else on the notes. Example 5 part B was a larger revision. I just swapped out the problem. I found one that just fit better for the notes and goes along better with the homework. So sorry for the last minute swap on there. Other major announcement is folks have been asking over the weekend about Valentine's Day. We're scheduled to have class on Valentine's Day, but since we're a night class, I decided to go along with what a few requests were. We're going to treat it as kind of a catch-up day. We won't have a formal class when we come back next Wednesday, but I'll still be available for office hours if you're on campus or through Zoom. And again, it'll be essentially just a catch-up day next Wednesday. I think that works out best for us since we're a night class. Any questions about that? Okay, I'll make this official by sending out another mass email to everyone in the class, just as kind of a reminder, especially on Wednesday, especially if you drive down. That's kind of horrible to come to an empty classroom, so that we'll know what we're doing. Then after that is President's Day on Monday. This one is scheduled. That's a national holiday, of course. So that means our next meeting after today is going to be Wednesday of this week right here. After which, I don't think there's going to be any other interruptions in the schedule at all. So we're just going to kind of get through it, aside from the spring break, of course. Any other questions, folks, with where we're at so far? Okay, I did change the due date on this to more accurately reflect when we'll be in class next. But if we don't finish these notes, we'll make sure that there is a full 1-week turnaround on these. However, if you're in the style of getting started with the problems early on assignments, I think after our work today, you could really get through just about everything here, if not the majority of it. But here's where we left off before the exam. Because we had the exam cut these notes in half, it might be a good idea to just refamiliarize ourselves with where we are at, what we're doing here. Essentially, chapter 14 started with, we used the essential limit theorem to create this diagram. And with some weird algebra with inequalities, we were able to say, not only is the sample mean within that value and this value 95% of the time, but upon rearrangement, we can create an interval where this is a defined and known number for the lower bound, same for upper here on the upper bound. And so we can say that with a certain amount of confidence, all thanks to the essential limit theorem, that unknown parameter mu will be captured in that interval with a certain amount of confidence we like to say. We don't say probability, we like to say confidence, because we're saying there is a specific probability that the whole method itself is going to be accurate, that mu is really in between or not. But we don't want to say there's a probability that mu is between like 5 and 7, because it either is or it isn't. There's no probability about it. It's very deterministic. It's the probability about the method coming out correct. So after seeing how this goes, what we did next was we refined what we did right here with the 2. We want to calculate the standard deviations more accurately, so we used z-scores. And this is a table that you could reuse if you wanted to for the homework and just use these values. They'll also be used later on in, I believe, chapter 19. But if you need to do something weird, like say 92% confidence, this is the method. We just go Q norm. This formula would work each and every time, and it would spit out one of these values here. After we had the confidence level, we went down to the full procedure. And here's what it looks like. If we want to have a, say, C% confidence interval for mu is going to be the unknown parameter. We have to know what sigma is for this method to work, so we'll see how to correct this in chapter 17. But here it is. We just take our best guess for the unknown value mu. That would be x bar. So we start with this point estimate that mu is approximately x bar. This estimate was useless to us until we described the error, but here it is. That's the error in making that estimate. And we have 95% confidence, if we select 95%, that the unknown parameter mu is really inside that interval. In fact, this part circled is so special, it has a name. We'll call m the margin of error. And so by definition, m is going to be z star times sigma over the square root of n. So that's the margin of error in making that estimate up here. Any questions at all, folks, with the confidence interval procedure so far? Okay, now that we have a confidence interval, we can go through a full problem. We started this one, but we didn't really get too far into it. So let's give this one a full and earnest try. And this will be our first inferential statistical method. Although we'll have a lot to correct when we get to chapter 17 because of that issue right there. But rereading the problem, the issue was in 2011, there was a nuclear reactor meltdown in Japan, the Fukushima reactor. After 4 months, they looked at how radioactive the fish were. We found these results, and they knew historically the radioactivity in becquerels per kilogram was supposed to be below 2 becquerels per kilogram. So there's a very noticeable effect after that meltdown occurred. The question was, do these data provide significant statistical evidence that the mean radioactive cesium tissue concentration is above 2 becquerels per kilogram? So we'll look for that evidence while we go through the problem. This is more something we're going to see more and more as we do more and more statistical inference. We're going to provide a complete analysis, which means really doing these kinds of things for the confidence interval. But you could think of this as really just a part A, B, and C we're going through whenever you see the so-called complete analysis. First thing we did is just restate the practical question. And I mentioned if you find the practical question in the problem, it's this right here, you're okay to just restate that verbatim, put it in quotes. That'd be completely fine. I think it's better to put it in your own words, but it's not completely necessary. Either way, you'd get full credit right here. And typically this is worth something like 1 point. It's not anything major, but that's a good way to determine what are we really doing in the problem. It gets us started. Pretty much everything we're going to be doing here is to try to support this step. I mean, that is the most important step in statistics. Nothing we do above here has any value unless we can give a solid conclusion that clearly communicates the results in a very non-technical way to anyone who has not taken statistics before. So that's our goal. And first thing we have to do then is define the unknown parameter. But really that was pretty much our first kind of problem this semester. We know we have to do this a lot, so we've been thinking about it along the way. The unknown parameter is mu for sure. You could, if you're typing this out, write it in as mu is always completely fine. If you like the equation editor, hit Alt and plus, then this slash and mu will give you a mu if you like, but that's only if you're into that kind of stuff. There's no requirement for that. Or you can just handwrite it like we've done right here. It'll always be up to your option. So I won't be too picky on how you format your results. The rest is going to be mu equals the mean. Now we have to decide mean of what exactly. A good thing you can do if the data is actually quantitative, like we are dealing with here, is just take a look at the data and find the units. The units of all these data is becquerels per kilogram. So say mu is the mean becquerels per kilogram of certain fish. Let's take a look. They were looking at 16 Pacific bluefin tuna. So we're thinking about all of them when we indicate the parameter. We're discussing the population now. So it's going to be the mean becquerels per kilogram for all Pacific tuna. Here's where it gets kind of hard, or tricky, I guess is a better word. This is right so far, but it hasn't really captured the problem just yet. The problem is about the actual meltdown happening and finding radioactive fish. So this isn't quite accurate just yet. We want to add a little bit more, but we don't necessarily want to copy in the whole problem either. It's okay to make it a little bit terse and kind of paraphrase things a little bit. So we might say, yes, it was the 16 Pacific bluefin tuna. They were captured off the coast of California 4 months after the meltdown. So maybe we'll say here, captured off the coast of California 4 months after the meltdown. Been more earthquakes in that area recently, so this is kind of a interesting problem to be studying right now. Now, some people might say this isn't quite there yet, because we might say which meltdown, but they don't happen too often. So I'd say this is enough context that we brought in that we're really talking about the spirit of the problem. The radioactivity of the fish was mentioned. We have to say the unit after we mention the mean. You have to indicate the population somehow. We're talking about all of these tuna off the coast of California, but those populations change with time. We're talking specifically as they were after the meltdown, 4 months later. There's a lot to capture inside there. And we were doing this as a homework question. It's never a bad idea or something you would not want to do. If you're not sure if you have the right parameter mu here, you could just email me what you've got and I'll be very happy to take a look at it. Because oftentimes, if we can't get this down pat, the conclusion makes no sense at all unless we know what the parameter even was. So that's like the hardest and most pivotal spot of the whole problem in a certain sense. Any questions at all, folks, about getting that parameter? Okay, now let's take another look at this. It says, provide a complete analysis. We have an assumed standard deviation. Maybe we should record that just for good reference. They told us sigma for the entire population is 2.95. What else do we have here? Let's see. We have a sample size of 16, so we might as well write n is 16 in this problem. Aside from that, I don't think we have any other good information. We're going to have to calculate our statistics ourselves to find out what they come out as. But there's still one last thing that we need to do on this problem. After we've come up with the parameter, we need to decide how confident do we want to be. It's kind of a weird question. A lot of the homework problems might say test at 95% confidence or something like that. But some of them are wide open. So we have to decide what's an appropriate level of confidence and what do we want to do for our problem. You could always come up here. These are the typical confidence levels. And this one would be kind of right down the middle. You're compromising with high amount of confidence and not making your confidence interval too wide around there. Being lower in your confidence, that's kind of a strange thing to do, but you could do it if you like. Or if you feel like the problem is really pivotal, the consequences could be dire one way or another, you might increase the confidence on it. But for these kinds of questions, it really is wide open. We can just decide on our own. In fact, let's leave it up to the class. Any volunteers for the level of confidence we should have on this problem? Let's go with 95. Awesome. So from the class, let's say we will estimate that unknown above, mu, with a 95% confidence interval. Well, you don't have to be that wordy. You could just simply say C equals 0.95 if you prefer, and that would do the job for this problem. But it's good to write this stuff out because it tells you what you're about to do. That's our intention in the problem. That's the reason we're doing any of this. We're trying to estimate mu. So next thing we're going to do is see if even the conditions are met. Now there's several assumptions that we have to check on the conditions. First thing we need is a random sample. If we don't have a random or at least representative sample, then our statistics aren't going to do anything for us. Our population is probably not quite right. So let's take a look. It says, here are the findings. Well, they didn't say much. A study examined the radioactive tissue concentration. Well, they did say it was a random sample. We don't know how they randomly sampled. There's got to be a pretty involved sampling method because they can't necessarily identify every single fish in the ocean, give them a unique identifier, and do a simple random sample. So they did some other kind of sampling design on this kind of thing. But let's just trust it was at least well enough designed that it could be, in essence, like a simple random sample. Giving that information, we might say for conditions, we do have a random sample. Of size n equals 16. So that's good for us. We know we are dealing with random data at least. We're in the right realm to deal with an inferential procedure. Other thing we might want to check is, well, how severely skewed is our data? That's always of extreme interest. If our data with that sample size 16 is at least roughly symmetric, then we're in great shape. But I would want to make a note that our author is assuming this for every single problem in chapter 14, that the variable came from a true and honest normal distribution. Because of that, the condition checking in this chapter is kind of minimal. We're just taking a preview of it. We should look for whether we have a random sample or not, but that's pretty much the only thing we can do at the moment. Nonetheless, as a preview, let's see how reasonable this assumption really even is. So we're going to assess the plausibility that the population is normally distributed. Based on having a small sample size, just 16 means our data could look a little bit weird, and that's okay. Weird looking data at small sample sizes still could have came from something normally distributed. I should mention here that this part is optional. And we'll start to do this in chapter 17 and more earnestly. In chapter 17, we will delve into the conditions really carefully to make sure that everything checks out. Here's just a preview of how it's going to go. First thing we want to do is actually import this data, and we have to do it anyway since we need some summary statistics from that data. So here's our quick refresher on importing data. You want to click on the little Excel sheet thing here. First option, then go wherever your data is. For me, it's going to be right here in this folder, for example 3. Then you should see the actual variable name in bold. All the data should not be bold. If that's correct, just click on import. Everything is working as intended. So there's our data. I usually click that away, so let's get rid of it. And all we need is, well, first thing we can do if you like, is extract that variable. Let's say rad for radioactivity gets example 3, then select becquerels per kilogram. So now we have all of our data imported. Next thing is just a quick hist for histogram. Rad will be the variable, but we probably want to give this a better title. Let's say for XLab, to stand for the X label. Let me make this a little bit wider. Let's see, what would be a good title? We might say radioactive cesium tissue concentration You could also include in becquerels per kilogram. But if it gets a little too long, you might have to paraphrase. Sometimes the title is just too long to really fit on your graphics well. And that's okay if you have to take some of that stuff out. Let's see how well it fits for that pretty long title. Not well at all. We've got unexpected string constant in hist somewhere right here. Oh, I can see the problem. We never actually put equals right there. That helps quite a lot. So let's say xlab gets that output. And there it is. You know what? That didn't do too bad. They just dropped it on another line. And as far as these data go, we have a gap here with a concentration of data from 6 to 8 becquerels and another concentration from 10 to 12 becquerels. It could be a sign of bimodal data, but keep in mind, sample size is just 16, so we don't have a lot of evidence in that direction. Now, at this stage, if you're looking at these data, it is absolutely plausible that they could have came from a normal distribution. That means if we were checking conditions in earnest, we'd be pretty happy looking at that kind of data. So let's pull it in. Without the red dot, let me move that over. Last try. There we go. So there's our display right here. This is optional, so that's why it's all in orange. If you skip this step in the homework, that's okay. But it's a good thing to get in the habit too. We'll say here that these data are, if I consider this to be the center, yeah, I'd say it's at least roughly symmetric with maybe a slight skewing to the left, but nothing major here. There's no severe looking outliers. We could use the 1.5 IQR rule of thumb, but it is just a rule of thumb that we have to keep in mind. If something looks visually like an outlier on this, say if this group moves clear over here, that's when we're more concerned and we might start checking for outliers using rules of thumb and such. We might say for this, these data are possibly bimodal. Bimodal is meaning we have a concentration here and here, and is fairly symmetric. What all this means is it's plausible these data came from a normal distribution. So that's a plausible assumption that our author had at the very top of the notes, his simple assumptions for the inference. But it's not the best assumption, like we mentioned. It's no guarantee that the population is distributed normally. In fact, it probably isn't. So when we get to chapter 17, we're going to turn this around a little bit and start using the central limit theorem. The central limit theorem is going to assert that the sample mean X bar approaches normality, irregardless of how the population itself is distributed. You just have to have a nice enough or high enough sample size. But here's where we are so far. And we can say overall, the conditions are met since, this is kind of silly to say, but it's up there in the conditions, so let's say it. Mu is unknown. That's silly in the sense that you would never do a statistical inference procedure if you knew mu. So it's got to be unknown. And the other condition is, and sigma is known. In order to use our confidence interval procedure, we have to know the value of sigma, or we might estimate it like they did historically. But with all that here, we have our conditions met. Now we're ready to delve into the actual confidence interval. It just says, carry out the necessary computations. Any questions first so far, folks, with looking at conditions? Okay, so for the necessary computations, really not too much is going on here. First thing you might want to do is just write down the procedure. It is X bar plus or minus this quantity, Z star, which multiplies sigma, divide by the square root of the sample size. So we have one thing missing. We still need the sample mean X bar, so we might as well calculate that right away. But everything else we can find or generate. For example, we know Z star. We found it up there on the notes. The problem stated what sigma was. Let's just focus right here on X bar first. So back over here in our studio, this will be pretty quick. We just put in mean, rad for the radioactivity, and it's coming out as a 10.3125. Then next we'll add and subtract this quantity, Z star. It's always a fast computation. In the notes, it goes like this. Once you decide on your confidence, just put in C gets 0.95. Next step will be Z star gets. I'll put a negative in front. This is going to give us the positive result. But keep in mind there's a plus and minus, so that's kind of irrelevant in a real sense. So Q norm, 1 minus confidence cut in half. And that's the full syntax. That will do the job for us. And if it doesn't work, keep in mind, it's also up there in the notes. You could just cite it and use it right away. Let me see, I got Z star as a 1.95996. And again, if you rounded this to 4 decimal places, it's just the 1.9600. Let's throw that in next. That's what's going right here in the next position, 1.9600. At the next step, let's just look up what sigma is. I believe they said it was, no, actually I forget, 2.95 is what they're telling us in this problem. So 2.95 would go right here. Final thing, the sample size was 16. So we divide by the square root of 16, divide by 4, essentially. So that's the whole interval. And I'll mention this again once we do this as a real exam problem. But if this was a real exam problem, and even if we made a huge mistake on the calculator, the interval is totally wrong, lower bound and upper bound. If this is on your paper, then I give a massive amount of partial credit for just that, because in a real sense, that is the interval. We still need to crank it out, but make sure you put this kind of work on your exam paper for the extra partial credit. Let me put this on the next page and let's crank it out on our next step. So now that we have all that together, really it's just a pretty simple calculator operation. Let's do it this way, as if it was a real exam question without using the syntax, and just pretend this is like a basic calculator you brought to the exam. Pretty much all I would do is take 10.3125. Usually we like to represent the lower bound first in an interval, so go minus 1.9600. In RStudio, you have to literally put in times right there, or else it's not going to know what you're doing with juxtaposition. Then 2.95 divide by SQRT, pulls up the square rooting function, and put a 16 inside there. So it probably looks a little bit different in this calculator versus yours, but same kind of thing. Here's the lower bound, 8.86, or 87 if we're rounding to 2 decimal places. So 8.87. At this stage, it's a good idea to put in the unit because we're about to interpret what we're getting here for the confidence interval. And even better, it's a good idea to say what you're estimating. The thing that we're estimating with that interval is mu. Putting it in here, right now, reminds us of that, and it makes the conclusion down below a lot easier because now we're looking at it. This unknown parameter is bigger than this value, 8.87. Then we just do it all over again. In your calculator, you probably don't want to type this in all over again. Just use second enter or something to call back your last entry. In RStudio, it's the up arrow. And just move over to this, change to a positive, and you'll get your upper bound right away. Upper bound is 11.76 upon rounding. So we'll go here and say less than 11.76 becquerels per kilogram. Move that just a little bit over. Well, I think we got it, folks. That's the lower bound, that's the upper bound. So we've done it. That's our first honest, well, sort of honest. Watch out for that thing in green. That's the thing we have to correct. But aside from that, that's our first honest confidence interval. Any questions at all, folks, getting to this stage? Okay, now as we go to interpret this, here's the thought that you'd want to have. We're not doing anything too different from what you did, say, in chapter 11. Let's take another look at here just for emphasis. In chapter 11, we did quite a lot of problems that went like this. Probability x bigger than 2 is some value. And we had to interpret that thing by saying, well, there's a 5.15% chance. We're going to say 95% confidence instead to change that up. But then we just went inside here and reinterpreted everything in words. We're fundamentally not doing anything different at all. We're going to have to look up what x is in this problem. It was written there. In our problem, we just have to look up what mu is. So let's take a really fast temporary screenshot. And here's what the conclusion finally looks like after all this work. Again, we have to assert we have a certain amount of confidence. It's not going to be probability or anything like that. We'll say with 95% confidence, then we just go on to the next statement. And the next statement is literally just reading all this out. It's probably good to start with the thing in the middle and just say is between lower and upper bound. So let's remind ourselves, the thing in the middle is this. This is the tedious part, but saying what mu is at the very start of the problem is always a good idea. And that's why I often ask it, and I apologize for the tedium of writing it down twice. That's the worst part about it. I'll cut that tedium down a lot on a real exam, so it doesn't feel like you're rewriting the same thing a whole bunch of times. But we have to say here with 95% confidence, the mean radioactivity in becquerels per kilogram for all Pacific tuna caught 4 months after the meltdown almost there off the coast of California okay, my hand's a bit tired, so let's take a break. So there's mu, and we can just say is between 8.87 and 11.76 becquerels per kilogram. At that stage, we can delete that, and we finally did it, folks. That is our full, complete conclusion to that problem. Any questions about it so far? Okay, our major requirements is it has to just be ordinary language. We do have to mention confidence right here. Again, it's worth mentioning why we say confidence right there. The issue with this is it's the probability that the whole procedure works is a 95% chance. However, if you replicate this study, you would be gathering another random sample of size 16. Your data is different, however, once you do that. If your data is different, so is your X bar right here. That's going to change. So if you do this 100 different times, this interval that goes from here to here, you will have 100 different intervals. They're almost assuredly different. But what we're saying is 95% of those intervals will have mu in between them. We paraphrase all of that by saying 95% confidence. So this is not the probability that mu is between here and here. It's just the probability the procedure works. That's why we convert to that language specifically in this scenario. Any questions about that so far? Okay, we'll have lots of opportunities to do these so-called complete analyses, and they do change. They get a little bit tricky in chapter 17, because where we're at right now, we just had the confidence interval procedure. So when you see a complete analysis, it didn't have to say what type of procedure. We just knew it was a confidence interval. In the homework, especially in the later chapters, watch for what kind of analysis it wants. Sometimes it's asking for a complete analysis with specifically a hypothesis test. Other times it's wanting a complete analysis with specifically a confidence interval. But now that we've talked about all that, let's go back right here. It said we want to estimate the average radioactivity of these fish. That's essentially what we did right here. The average radioactivity for the whole population is somewhere between here and here. There's another part of the question where they asked, do we have significant evidence it's above 2 becquerels per kilogram? And we can say, most definitely. The confidence interval doesn't even include 2 becquerels per kilogram, then we do have that evidence. So as an additional comment, let's say here, these data provide significant statistical evidence that the population mean is above 2 becquerels per kilogram. So we have that evidence strongly for sure. Any questions at all so far? Okay, I want to add a little bit of a weird change here. I'm going to undo it in a moment, but this is something that's kind of interesting about confidence intervals and statistical significance as well that we'll start to see with hypothesis testing. If the question wasn't 2 becquerels per kilogram, maybe it was 9 becquerels per kilogram, we would say the data do not provide that significant statistical evidence any longer. And the reason is 9 becquerels per kilogram is inside this interval. So that means it's plausible that mu takes on a value of 9 if it really is between here and here. So we only have significant evidence if the whole entire interval is larger than that value in question or below that value in question. If the questionable value is inside the interval, we lost statistical significance in that case. But we should probably Control Z that off there. Just a side comment. But let's now take a look at some other interesting things about confidence intervals, and we'll probably end class looking into hypothesis testing. Any questions at all so far? Okay, I'd say this part of the notes is a little bit tricky, but this is meant to help us with the homework as well. Some of these questions could also come back on our second exam, but by that time, they're probably going to look pretty familiar. So all these are now just concept questions about confidence intervals. It says to start, suppose we have a 95% confidence interval. This one's written in the form from A to B for the parameter mu. You could change that up if you like and say A less than mu less than B. But in mathematics, sometimes we just write it out as an ordinary interval using interval notation rather than inequality form. So we have an interval for estimating mu. And for the first question, it says, for true or false, if we randomly select an individual from the population, there's a 95% chance the individual is in that interval from A to B. How do folks feel about that? Does that feel true or does that feel false so far? Any volunteers over Zoom? Does this seem like a true statement or a false statement for folks in Zoom? Some say yay, Eddie's for nay. It's kind of tricky in a certain sense, right? And To me, it almost feels right, but it turns out there is something wrong with this statement. It's about that mu right there. That mu is the mean of the entire population, and that means it's involving everybody, not just a single individual. If we want to interval for a single individual, it turns out those intervals go way, way wide. And those are very, very wide intervals altogether. It's the mean that we have a little bit more certainty with, and the interval settles down to something more practical. But there's really a couple things wrong with it. We wouldn't say 95% chance either. We'd say 95% confidence. So there's two things wrong here. Let's indicate them both. I'd say the glaring thing is talking about an individual. So let's say here, false. The confidence interval is for the mean of the entire population. Not an individual. And we should have said 95% confidence, not 95% chance. Let's say that down here. We should also say 95% confidence. So that's our first concept question here. And really the big takeaway with this one is the interval is about the average for the population. It says nothing about individual to individual values. Next one's kind of weird in a certain sense. It's also silly, I'd say, in the same certain sense. How about for this one, folks? For true or false, we did a 95% confidence interval. Is there a 95% chance X bar is in that interval from A to B? Or is it a different chance? Any volunteers on that one there? It is true. Actually, it's kind of semi-true depending on how you interpret it. It's more of a 100% chance, really. But this is in essence a true statement if we just bump up that probability there. So I guess it depends on how we answer it. We can say here, true, as long as we say there is a 100% chance. X bar is in that interval from A to B. I feel like that deserves some explanation, but the explanation is really fast. Pretty much all you do is you write down the confidence interval, x bar plus or minus critical number z star times sigma over root n. But if your confidence interval takes this form, not only is there a 100% chance it's in that interval, it's also the dead center of that interval. So this is just kind of a weird concept question about reminding us where x bar even factors in to creating the confidence interval. So let's say here, just as a related thought, in fact, x bar is in the center of the interval. That deserves an exclamation mark since that's pretty much what part B is all about. Next ones are a little bit trickier as well, but these are kind of fun to kind of guess and see what could happen. Then we'll try to explain if we have the right reasoning. First one says, well, maybe we did a confidence interval and it was wide. We might want to do something about that. And let's say we increase the sample size. Would that indeed make the confidence interval narrower, or would it make it wider if we increase the sample size? Any volunteers for which way it should go? Wider or narrower? Narrower. That's a hard word. It turns out it wouldn't be wider on this one, but what would happen is it's all about what goes right there. If we make the sample size larger, that quantity gets larger, slowly because of the square root. But if n gets larger there, this whole thing is going to get smaller. Your denominator is getting bigger and bigger. You are having less of a quantity in here. But that means this entire thing through multiplication is also getting smaller all at the same time. So if we increase our sample size, that gets smaller, which means the interval would get narrower. But that's good. What we want is the narrower intervals. That implies more accuracy in our estimation. So for here in our explanation, we can say if n gets larger, the margin of error which is z star times sigma over the square root of n. We want to focus pretty much right here. That's what's causing everything to change. Get smaller. Oh, let me put that away. Get smaller. And so the interval becomes narrower. And that's good. That makes sense, right? If you have a larger sample, you should have more accuracy in your study. And more accuracy is related to intervals by them becoming narrower. But the downside is, if you want to make your interval really, really narrow, because of that square root, you have to bump the sample size a lot just to cut the interval in half. So that's one area where we're pretty much just punished by algebra at that location. So there's a limit to how accurate we can actually be in some sense because of that. Well, there's a lot of highlighting there. Let me take that off. So that's how it goes in part C. Then in part D, it says, I think this one, in my opinion, is a little bit trickier. If the confidence level were to decrease to 90%, that's not a good thing, right? You want to be more confident if you can. But if you made your confidence go down, would the resulting confidence interval become wider or narrower? Any volunteers over Zoom? Would this be wider or narrower if our confidence level decreases? Aspen says wider, as well as Abby. Any other volunteers? I agree with folks in the sense that that's what should happen. And here's where statistics gets a little bit weird. If we decrease, that's something bad. We should be punished, right? And punishing means interval becomes wider. But it turns out it's not true in statistics. This is essentially why we always insist every time you do a confidence interval, this just has to be there somewhere. Usually it's a first statement. We are at this amount of confidence. Because it turns out, if you decide to be less confident, say, instead of being 95% confident, we went to 90% confidence, the critical number z star, it does control the width of the interval, it goes down. That means your error interval became narrower the less confident you were. That's weird, right? You're like being rewarded by being not very confident at all. In fact, we could take this to an extreme and say, let's use the code for this. It's, oh geez, we don't want to do that. Let's use this syntax right here. Once I get a good window, let's move it over like that. And let's put in, say, 10% confidence and just see how weird that gets. It'd be Q normed, 1 minus 0.10 divided by 2. And that was apparently invalid. Let me try again. There's something wrong in there. I'm not finding it. Weird. Hey, I'll give you one moment. Let's see if we can fix this issue here. Does this syntax work? So Q normed, 1 minus 0.10, we're going to be 10% confident, divide by 2, and there it goes. This time it works. I'm not sure what I did differently. But if we were only 10% confident, our critical number turns into a 1.1256. It's diminished by a ton. You can make your interval as narrower as you would like and just make it look like your statistics were amazing. You have a very precise response or estimate. But if we always report the confidence first, that kind of shenanigans is eliminated. And so that's the reason why, again, we like to report the confidence first, because this is extremely counterintuitive. Doing something like dropping confidence, which is bad, rewards us with a narrower interval instead of a wider one. So let's mention it all here. If confidence decreases, then let's now talk about that critical number Z star right here. Z star decreases. Making the confidence interval narrower. But that's not ever a good reason to make your confidence interval narrower by dipping down your confidence. We want it narrower, we just have to bump up the sample size and just stick with the confidence that was initially indicated for the study. Well, any last questions, folks, with that part D? Okay, part E is more of just a reminder that we've been harping on here and there as we've gone through the notes. It says when we give a practical conclusion, we state the level of confidence, the confidence level, but we don't consider the confidence level of probability that mu is in that interval. It asks us, what does the confidence level represent? And if this is, say, a concept question on an exam, it's actually a pretty fast one. You can just simply say the confidence level represents, I think it's best to say it's just a success rate, essentially. Represents the success rate for the method that produced this interval. Well, that's the rundown for the concept questions as far as confidence intervals go. I think they're a little bit tricky, and hypothesis tests gets a little bit trickier still. That's why we're taking extra time in chapter 14. It is just an introduction to inference, and so in a real sense, this is also kind of where the course starts. Chapters 1, 2, and even 11 were more everyone getting on the same page. And now we're finally in pretty deep in the weeds, and we'll take another look at hypothesis testing next. Well, let's put this maybe on the next page. As far as hypothesis testing goes, in a real sense, you're not doing anything fundamentally different as long as you're using that test right there. This one is sometimes considered the gold standard or one of the more important hypothesis testing because it's going to account for a difference in two different directions. If you're doing a confidence interval and that one hypothesis test, your conclusions are always the same. So that's kind of nice in a sense. However, these are the weird ones. Now, your confidence interval conclusion and those tests do not have to be the same. But before we get into all that, let's also start calling some of these by their proper names. The very bottom one right here is sometimes referred to as a two-tailed test. The one on the top, this one would be the right tail test because of the direction of the inequality. One below would be the left tail test. So this one is a right tail test. And next one is going to be the left tailed test. So that's our setup so far. When we go to set up hypothesis and hypothesis testing, we're really doing two things at once. We have to set up a so-called null hypothesis. That's the so-called claim to be tested. And if we were watching, say, court TV or something like that, a null hypothesis in the court of law, they use this exact logic. is that the defendant is not guilty. That's their working assumption throughout the entire proceeding of court. And same with hypothesis testing. We define a null hypothesis and we stick with it, whatever it is, through the entire statistical analysis. Then we just look at how compatible is our data with this claim. If we keep on piling up more and more data that makes not guilty seem implausible, maybe I'm in, say, traffic court and they have TV or video camera footage of me doing 100 miles per hour through a school zone, then my statement of having not any guilt is not compatible with evidence. We'll have to assume that the alternative hypothesis is the one that's true. In hypothesis testing, we're doing exactly that. We set up a claim to be tested, the null. Sometimes it's a value of a population. The population has a value of 2 becquerels per kilogram historically, but alternatively, maybe it went up. So if our data is not compatible with this, we'll use probabilities to see how compatible it is or not. We assume that the alternative hypothesis is true, and that's how we're going to do our logic of hypothesis testing. But this is a big reminder. We'll harp on it a lot as we go throughout the notes. Even in a court of law, suppose we make this working assumption, Mike is not guilty for speeding, and I actually get off. That's wonderful. It does not mean the court has proved I didn't speed. Not at all. That's not even the objective of the court, is to prove my innocence. The objective of the court is to see if this is even a reasonable assumption. So even if we fail to reject the null hypothesis, we'll never write a conclusion that says it's true. That's always false. And same with court. If someone got off clean in a court of law, we didn't say the court proved the innocent. They just didn't find enough evidence to say that this became implausible for the jury. So we'll harp on that quite a lot. And now there's a lot of ways we can write our hypotheses. Notice it always involves a population parameter. So you can't put X bar here, you can't put S. It has to be either mu or P. These are the only two parameters. Well, there's others like, say, sigma, but we're focusing on that a little bit less. These are the two major parameters that we're focusing on. We'll use mu if the data is quantitative. And we use P if our data is a specific kind of categorical, only 2 outcomes. So categorical with 2 outcomes is whenever we use P. So we have to decide before we even form hypotheses, what kind of data do we even have? Is it categorical or is it quantitative? Then the research question of the problem is going to tell us, are we doing a right tail test? Are we testing if the parameter is greater than, less than, or are we looking for any difference from the null hypothesis statement? So we choose these based off the actual context of the problem. If we don't find any context that tells us it's this one or this one, we go to the two-tailed test. The two-tailed test is the default. So in other words, you need strong reasons to use this test. Oh, that's weird highlighting. You need a strong reason to use this test. The problem has to literally tell you you're testing for that direction or the one down below. I think that's an important enough concept. Let's put that in as an actual note. That last one is the default. The two-tailed test is the default. Well, we're just about there, folks. Once we talk about the null hypothesis, we say the population parameter is equal to some hypothesized value. And this is already kind of weird depending on how many statistics you've taken. In particular, for folks who are also in the biometry lab, you're learning statistics from different source materials. Our author always puts equality there every single time, no matter what, whether there's a right tail test or a left tail test, our author is always putting equality directly there. Now, not everyone does this. Sometimes if you're doing the right tail test, you put less than or equals to right here. If you're doing, say, the left tail test, you do greater than or equals. For our class, I'm happy to take either way you write out your hypotheses. The major thing is, notice your alternative always involves either strict inequality or non-equals. It's the null that has equality, or maybe a less than or equals, or maybe a greater than or equals. That's always going to happen in the null. Well, that's a lot of talking. Let's do our own hypotheses and try to put all these ideas together. Let's scroll to about here. What I have are just some simple scenarios where we're going to state what the parameter is, what the hypothesis should be. So define the population characteristic. Oh, that should have said parameter right here. Let's put that in as a quick edit. Some people like to use the word characteristic rather than parameter. I like going this way, it's just faster to say. We'll write the null alternative hypothesis in terms of that population parameter values. That's a weird edit to fix twice. Sorry about that distraction. Well, let's give it a try. Again, there's not a lot of context here, so we're focusing primarily on the hypotheses this time. It says seatbelt compliance in Massachusetts was 65% in 2008. The state wants to know if it has changed. So from all that, we need an alternative hypothesis, a null hypothesis. We need to state the parameter value. But let's also go like this to start out. Is our data quantitative or categorical based off just this information? One way to think about it is, let's imagine if you collected a database on each one of these drivers. Are we collecting a number or some kind of categorical response? I'm sorry for missing the chat. I agree with Hedda, this is definitely categorical data. Pretty much what all the data is going to be is, just like you said, yeses or nos, whether they were in compliance or not. So we have absolutely categorical data. And that percentage right there is kind of a giveaway sometimes. If all you have is a percentage, well, that's the percentage that someone is in the yes category. So we've got categorical data. That means our parameter is going to look like this. It's going to be a P for a population proportion or population percentage. When we go to write it out, though, it's super confusing because P is typically unknown, yet we're looking at it right here. However, that's the 2008 value. We want to know if it's changed from the 2008 value. So this is how we typically start. It's a good idea to identify this value first because that is the hypothesized value. Notice it's everywhere in your null and in your alternative, however you write it. The way it's indicated as a formula is, in notation, is P naught. P naught is the hypothesized value. And we found that it is a 0.65 in this problem coming from right here. But it is not P. We have to write out P using ordinary words and not actually assigning it a value. Because it's categorical data, you might start with P equals population proportion, and then we just go from there. It's a proportion of something. Let's see, we're talking about drivers in Massachusetts being compliant with seatbelt use. So let's say population proportion of Massachusetts drivers compliant with seatbelt use. But if we end it right here, it's no different than the 0.65. It seems like we're just restating things. What we should say is currently, or presently, or in the current year. Anything along those lines are saying we're looking at the specific population as it is presently. Let's say here, in the current year. Wherever year this study was intended to run, maybe 2024, probably more like 2009 or something like that. So that's our hypothesized value. That's the population proportion. Next thing we're going to do is write out H naught. Here's your null. HA is your alternative. And they both talk about your population parameter as your portion that goes here, here as well. They're referring referring to P, not the P naught. So there's a statement about P for both the hypotheses. This is now read as a null hypothesis. We don't put equality here, it's just a statement. So we typically put a colon. We'll put here P equals. But over here, we have to make a choice. It's either going to be a less than sign, a greater than sign, or a not equals. So we're either doing a left tail test, a right tail test, or a two tail test. Sometimes there's a word that directs us to us, and there is a word this time. Any volunteers for which test we're going to go for? I'd say the words that we want to look at is right here. Because that could have been rephrased as the state wants to know if it has decreased. That would be a left tail test. Or they could have said, state wants to know if it has increased, the drivers are getting worse. That would be the right tail test. But the state is now identifying, well, they don't know. They're going to test for either direction. And honestly, that's probably sensible. We're going to determine if it's gone down from 65% or up from it. And from that wording alone, that's why we'd use this. If there was no word that directed us to one test or the other, we would still use the two-tailed test with the not equals because it's our default test. We need more wording here to direct us to a less than or a greater than. But once we have that, we're pretty much all set. We take this value, the 0.65, the value to be tested. So that's the hypothesized value that goes in all of these. That copies in directly right here. 0.65, 0.65. So that's pretty much our statement of hypotheses then. The null hypothesis is a statement that nothing has changed, much like saying the defendant is not guilty. The alternative hypothesis saying, yes, something has definitely changed, potentially drastically. And this is like the statement of the defendant is guilty. What we would do now is start collecting data, calculating test statistics, and we'll use probability to see how in line is our data or how compatible is it with the null. A small probability would say it's incompatible, and the alternative hypothesis is the right statement or the right conclusion for the population. So just stating these hypotheses is kind of an adventure. Any questions at all, folks, on getting those two down? Okay, to state the hypotheses, you really need a few things. You need to know what is the question, what are we testing, or what are we comparing against, like this value here. Then you have to be able to determine the right data, whether it's quantitative or categorical, because we have to write this thing out. And it makes sense because that's what goes right here. This is always the research question. We're looking for evidence to show that this is true. So if we find that evidence, we'd be able to write a conclusion by saying P, whatever it is not equal to 0.65 in our study. We have that evidence. But not knowing what P is makes that conclusion extremely tough. So just like with confidence intervals, a lot of the action in interpreting our work is right here when you define your parameter in the very, very beginning. But that was so fun. Let's try it again with our next problem. So next one goes, this is the one that got completely reworked. One of the reasons I reworked this part B was above problem is for categorical data. I thought we ought to do one for quantitative data. It makes a lot of sense. And also it was kind of a simple problem right here. This one is more of a real problem that we'll actually do in class. In fact, we considered this data at the start of the class on week 1. So let's take another look at it. It says the ankle brachial index, ABI, compares blood pressure of a patient's arm to the blood pressure of a patient's leg. ABI can be an indicator of different diseases, including arterial disease, and a healthy ABI is 0.90 or greater. You know, they're giving us a hypothesized value essentially when they say that. So let's write that in as not a P naught this time, or the parameter is not P. This is quantitative data. So we'll say mu naught, hypothesized value, is 0.9 in this problem. So that's our value to test. It now goes on to say, in a study by these folks, the researchers obtained ABI of 187 women with peripheral arterial disease. Results were a mean ABI of 0.64. Although they gave that to us, that's not what's going to go right here or here. They gave us a statistic, so that's X bar. That goes nowhere near our hypotheses. Same with the standard deviation. We can't do anything with that. What we have to write down is, what is mu? And then we go from there. So let's actually, just to be careful, put in X bar is 0.64. S is 0.15. We're using the symbolisms we would use for statistics because they're saying the results, they're describing the sample of the 187 women. They're not describing the entire population. So we have some statistics down. We might as well put in N equals 187. And this thing will be very interesting for us. When it says the 1% significance level, we'll be describing this a little bit better in chapter 15. But this is our benchmark for saying we have enough evidence to reject the null hypothesis and support the alternative. We want a certain probability to be below 0.01. So that's our requirement of evidence. Well, let's say what mu is. We did it once at the start of the semester, but it's been a while. We'd say mu is the mean ABI, ankle brachial index, for all women with, now this is kind of confusing in a way. When they gave us this value, we're talking about a population of all healthy adults, it looks like. That's not our population. We need to refine to the fact that we're talking about, let's see here, specifically women with peripheral arterial disease. That's a completely different population. And the sample of 187, that's just, well, another separate thing. That's the sample size. We need to say for all women, not just the 187, with peripheral arterial disease. So now that we have a parameter down, we can start stating our null and our alternative hypotheses. They're both going to be in terms of the unknown, so we drop them both in. And before we get too far, let's settle down what's going on with the alternative. If you notice that there's a question mark, they're probably talking about the alternative. That's the research question in a certain sense. So take a look. It says, at the 1% significance level, do the data provide significant statistical evidence to conclude that, on average, women with peripheral arterial disease have an unhealthy ABI? Here's where we have to do a little bit of loophole jumping. An unhealthy ABI can be conflated with having a healthy ABI, which is 0.90 or greater. So the moment they said unhealthy ABI, they're asking us for us to test in a specific direction. This one's a left tail test, and it came from this right here. Does that make sense to folks on why we went directly with the less than? Awesome. They could have reworded this whole thing. Maybe they could have thought, well, we don't know what's going on with peripheral arterial disease. It could go up or down from the amount right here. If that's the case, they might have said, at the 1% significance level, do the data provide significant statistical evidence that on average, women with peripheral arterial disease have an ABI different from 0.9. They say it that way. We have an inequality here for a two-tailed test. But they said unhealthy ABI, so that's going to be less than the 0.9. Next, all we have to do is go take the hypothesized value. It goes here and here. But this is where it gets kind of interesting. Our author will always put equality here, no matter what the situation. And sometimes that is kind of counterintuitive because the null and the alternative should be direct contradictions of each other. If you negate this statement completely, you flip around the direction, And it looks like this. So if some folks want to write their null hypothesis in this way, that is logically appropriate, and that's what about half the people in the nation do with their hypotheses. The other half go equality here every single time. But I just want to emphasize, I'll take it for full credit both ways. There are good reasons for doing it this way. We'll see it in chapter 15, and good reasons for doing it the other way. It's kind of unfortunate. There's two good ways to write that. Well, looks like I have definitely ran out of time, however. Any last questions, folks, before we call it a night? Okay, so this is kind of our rundown on getting started with hypotheses. When we come back on Wednesday of next week, we'll do it in earnest, work through the full test, and see how it goes for another complete analysis. But this will be our stopping point. Have a great night, folks, and I'll see you all next week. Thanks, folks.